So good evening everyone. Today we will start with chromatographic techniques. The word chromatographic, it comes from the word chromatography. Okay. Now this chromatography is, again, it can be broken down into two words. Chroma means color. So why color? Initially the chromatographic techniques, they were used to segregate pigments from the plants. Okay. On the other hand, the word graphy, the meaning of the word graphy, it is to write. Okay. So what does this mean? This means that we are analyzing the color pigments on a specific piece of instrument or a device. Okay. So depending upon the information what the colors will be generating, based on that we usually go for the separation or the analysis. Okay. The chromatographic techniques, it is basically a technique for the separation of the analytes. Okay. Chromatographic techniques, they are used for the separation of the analytes. Now when we call these analytes, there may be a mixture of analytes, and in general we can call it as separation of analytes present within a sample. To understand what chromatographic technique does, let us take a physical example. Say for example, you have three groups of people, A, B and C. Consider you and your family in the group A. Okay. Now you have thrown a party at your home. Okay. So in that party there are people who are in the group B and they are close to you, very close to you. Whereas in the group C there are people where you have who will be close to you but not as close as that of the people who are in the group B. Okay. Now you have thrown a party in your home. Suppose this is the home. So what is this basically? This is, in terms of chromatographic technique, we call it column. Okay. In the case of column chromatography. Okay. The casing or the home, it is regarded as the column. Okay. So within this column, you and your family members, they stay all throughout. Okay. So during the party, what you are doing, all of your members, they will be present and they will not change their properties as such. Okay. So you and your group members or your family members, they are regarded as stationary phase, because you are not changing your property, and it is expected that throughout the party you will be present over there. That means you are a stationary factor during the party. Okay. So this A, they are stationary phase. Okay. Then you have invited B and C group of people. Okay. Now these groups B and C, they are corresponding to analytes. Okay, B and C, they are corresponding to analyte, and combinedly we call them as sample. Okay. Now, when you are doing a party, there is an independent variable. What is that independent variable? The independent variable in that case is time, and we say that time flows by. Okay, time flows by. Okay, so the time in your party, it is corresponding to mobile phase in chromatography. Okay, now what we do, we inject the sample within the system. Okay, and they are coming. How the sample is being injected within the column? In our example, we are injecting it with respect to time. Okay, we are diluting it in a time, because the persons, they are coming at their own what you call specific time. Okay, so the B and C, they are coming inside. Okay, now if you take another independent factor which is related to time, and let us talk about it as the experimental time. Okay, when we are starting the experiment, because here we have taken the time as the mobile phase, so let's take another independent variable, experimental time. So within the mobile phase B and C, we have dissolved, we have entered this sample within the column. So slowly what will happen, these analytes, they will start coming downwards due to the action of the gravity, and we will be getting some effluent. Okay, we will be getting some effluent. Now what we said initially, the C analyte or the C group of people, they are not very close to you. So what will happen during the party? They will be the one who will be moving faster, and they will be moving out very quickly. So the C will come down very quickly. Okay, and suppose at the exit of your home, if you keep a detector, what will the detector see? The detector will see that you have initiated a party at 0 time, at 0 experiment time. Your party has been going on within this period, and during that period B and C both were present within your home, and after a particular time there will be an increase in the count of the people who are going out. So the persons who are having lower affinity with you, that means the analytes which are having lower affinity with the stationary phase, they will be going out quickly. After that, there will be again some time duration which will be there. Then you will be having another peak associated with the B group of people. In the B group of people, what you will be having? You will be having the members or the relatives who are closer to you, and they will be leaving bit later than the C group of people. Okay, and then again you will be having the baseline like this. So while we have been discussing about this party example, we have talked about certain points. The first point we talked about the column. So in a chromatography, there will be a housing or there will be a base. Okay. So the housing or the base, it may be a column, it may be a TLC plate over where you will be applying some silica gel, or it may be in a very simple case, it may be a filter paper where you go for the filter chromatography. Okay. Then second thing what we talked about, second thing was the mobile phase. Okay. Yeah, sorry, the stationary phase. The second point is the stationary phase. So in the filter chromatography, the base itself is a stationary phase, or if you soak the filter paper with some solvent, then that solvent, it acts as the stationary phase over there, because it is to stay on the base forever. Okay. So we have the stationary phase. Then we have a mobile phase. The mobile phase, it will be dissolving the sample, and the sample, it will be containing the analytes. So the analytes will be dissolved, the fourth part, the analytes, they will be dissolved in the mobile phase. Okay. Now what is happening over here? You are giving this, you are starting or initiating the mobile phase plus your sample injection. Okay. Sorry, sample. You will inject it, or you will start purging the system with mobile phase plus sample. Then after certain period of time, you will be getting C, and then say C analyte, and after again certain period of time, you will be getting the B analyte, and we will be getting a graph something like this. This is time, this is your concentration. Okay. So why I have got this smaller peak over here? Because when your mobile phase is moving, so what is happening? It will come first. So your detector will see that something is exiting the system. So the first peak what you will be getting, it is associated with the mobile phase which is getting out of the system. Okay. So this is called the mobile phase peak. This is associated with the mobile phase peak. Then you will be getting the analyte which is having lesser association or lesser affinity with the stationary phase. Then you will be getting another peak which is having lesser affinity, slightly higher affinity to the stationary phase as compared to the C type of analyte. And if there is a mixture of 4 or 5 analytes, then you will be getting subsequent peaks over there. Now if you see the whole of the experiment, it is taking place in the time domain. It is taking place in the time domain. Okay. Another important thing, another important part of the chromatographic system is the detector. Okay. So detector, we have previously talked about various types of analytical methods. So detector may be one, UV visible spectrometer, two, it may be IR spectrometer, okay, three, it may be NIR spectroscope. Okay, so whatever the spectroscopic methods, rest of the spectroscopic methods we have discussed, we can use over there. Apart from that, there is another method which spectroscopic method which we'll be discussing later on, and that method it is regarded as the this mass spectrometry, MS. MS means mass spectrometry. Okay, we can use it for say AAS, atomic absorption spectroscopy, atomic emission spectroscopy, and whatever the spectroscopic techniques we have talked about, any of the system, it can be used as the detection system. However, in most of the cases you will find either the UV visible spectrometer or the mass spectrometry for the analysis of the analytes while you are attaching it with the chromatographic system. Okay, any question? No, good. So what is chromatography? As I already told you, it is a technique where we are going for the separation of a mixture. Mixture of what? Mixture of analytes. Okay, so the mixture is dissolved in a fluid. The fluid, what it is? It may be a gas, it may be any kind of solvent, including water. Okay, including water, and that fluid where we are dissolving our analytes, it is called the mobile phase. So what it does, what is the function of this mobile phase? The function of the mobile phase is that it carries the analytes through the chromatographic system. Okay, which may be a column, which may be a capillary tube, it may be a plate, it may be a sheet, okay, on which is fixed a material called the stationary phase. And what is the stationary phase? Stationary phase is the phase which will be having an affinity for the analytes. Okay, differential affinity, in fact, not only affinity, differential affinity. Okay, so this is an important point. The stationary phase, it should have a differential affinity. Because if there is only a specific type of affinity, that means it will not be able to segregate the mixture, because it will hold both the type of analytes for the same duration. Okay, differential affinity means when the stationary phase will hold the analyte, different analytes, for specific period of time which is characteristic for that analyte. Okay, so in our case we are having the host system, and the host friends, the general friends, they were in the category C, so they were having a lower affinity as compared to the type of group of people who are present in the B. Say for example the close relatives. So usually you will find that in a party the close relatives, they leave the party quite late. Okay, so herein we can see there is a differential affinity between the host and the group of people, and this kind of interaction, the differential affinity towards the stationary phase by the analytes, should be there. Otherwise your chromatographic system, it will not be able to segregate the analytes in a proper way. Okay, now this different constituents of the mixtures, they have different affinities for the stationary phase. Okay, the different molecules stay longer or shorter on the stationary phase depending on their interaction with its surface sides. So they travel at different apparent velocities in the mobile fluid, causing them to separate. Okay. Now the separation is based on differential partitioning between the mobile phase and the stationary phase. Now herein we have used one important parameter, differential partitioning. Now what do you mean by partitioning? Most of you have heard of the word partition coefficient. What is the partition coefficient? For determining a partition coefficient for a solute, we need to have two solvents one solvent should be polar in nature, and usually it is water, and the other system, it should be apolar in nature, okay, and it is usually 1 octanol. Okay, so usually partition coefficient, it is being determined using two solvents. In general, if you just want to find out the distribution of the solid analytes or any specific compound, partition coefficient of a specific compound, then we use water and 1 octanol, and it is basically used in most of the pharmaceutical compounds. Which we call as API. So if you have some APIs, active pharmaceutical ingredients, then if we want to find out the partition coefficient, then we usually use water 1 octanol system for determining the partition coefficient. Okay. Now what does this say? It says how the solid or the compound for which you are trying to find out the partition coefficient, they are getting distributed within the water and the 1 octanol system. Okay. Now usually the partition coefficient, it is only associated with the undissociated compounds. Okay, that means we try to find out the concentration of the compound, say A, in the undissociated format in octanol OCT divided by the concentration of the same analyte in the undissociated form in water. So this is the basic definition of a mathematical definition of the partition coefficient. However, practically it is very difficult to find this thing. Hence, there is another terminology which is regarded as the distribution coefficient, and it is quite interchangeably used with the partition coefficient, and it stands for the concentration of A in octanol divided by the concentration of the A in water. So in the case of distribution coefficient, what we do is that we use both unionized plus ionized compounds which are present in the octanol, and similarly in the A also, whatever the ionized and the unionized compounds are present, we consider that. That means we only consider the amount of the analyte present in the octanol and water. We do not consider it whether it is ionized or non-ionized. Okay. So it is the ratio of the concentrations of a compound in a mixture of two immiscible solvents at equilibrium. Okay. So this ratio is therefore a comparison of the solubilities of the solute in these two liquids. The partition coefficient generally refers to the concentration of ratio of unionized species of compound, whereas the distribution coefficient refers to the concentration ratio of all species of compound, ionized plus unionized. Okay. Now, how it is determined? Can anyone tell me how it is determined? What we do is that we dissolve the solute in one of the solvents, say water or octanol. It is one octanol. Okay. So in whichever solvent it is dissolving, we dissolve the analyte or the compound in that solvent. Okay. Then we add the solvent or the solution, not the solvent, sorry. We add the solvent in a specialized apparatus which is regarded as separating funnel. Okay. Say for example, I have dissolved A in octanol. So what I will do? I will put this API solution, okay, within the separating funnel. Say I have used 20 ml of the solution. Okay. Then what I will do? I will add in the next step water. Okay, it will be there. So we have water and the octanol. Now since octanol, it is hydrophobic and it is having lower density as compared to the water, so water will settle down. So we will be having water at the bottom and we will be having the octanol on the top. Okay. Now we will be having this tap which will be in the closed position initially. Then we will be putting the cap or blocking the this inlet port, and then we will be shaking it for say 15 to 20 minutes or 30 minutes, whatever is your protocol. So we will be shaking it. Why we are shaking it? We are shaking it because in that case, while we are shaking it, we will be forming an unstable emulsion. And while this unstable emulsion is formed, what will happen? There will be an increased surface area so that there will be transport of the solid from one phase to the other. Okay. So after doing that, we will be keeping this separating funnel at a proper location and in an undisturbed fashion. Say for example, for 3 hours. Okay. So since we have not added any emulsifier, and due to that reason, the emulsion that was formed, it is unstable, they will start separating from each other and there will be a phase separation. And due to that phase separation, we will be again having an aqueous layer at the bottom and the octanol layer at the top. Now we will collect a portion of the water from the lower this tap by opening the tap or the the sampling port. We will do that, and by removing the top cord, we can sample out the octanol from the top. Now we can measure the concentration of the analyte in both octanol phase and the water phase, and by doing that we can find out the concentration of the analyte in octanol and water. Okay, so what is happening in the chemical and the pharmaceutical sciences? Both phases usually are solvents. Most commonly one of the solvent is water, while the second the hydrophobic phase is there, and it is usually the one octanol. So hence the partition coefficient measures how hydrophilic or hydrophobic a chemical substance is. Okay, higher the hydrophobicity, you will be having a higher amount of the analyte distributed within the octanol phase, and lower amount of the analyte will be present in the aqueous phase. क्या सोच रहे हो? Lost in some word? Okay. So it is quite possible that one of the solvents is a gas phase and the other it may be a liquid, and in that case we will call the partition coefficient as the gas liquid partition coefficient, which can also be determined. Okay, and usually this kind of partition coefficient, it is used in gas chromatography. Okay, gas chromatography. Now partition coefficient, as I told you, it is P, which will be in octanol divided by concentration of A in water. Okay, however we usually put it in the form of log. If P, if it is greater than 1, it is hydrophobic, and P, if it is less than 1, it is hydrophilic. Okay. So chromatography, it may be of two types. It may be either preparative chromatography or analytical chromatography. The preparative chromatography, it is used in a large scale. Okay, and since it is being performed at a large scale, it is used for the purification of a specific compound. Okay, it is mainly used for the purification of a specific compound. Preparative chromatography, it is used to separate the components of a mixture for later use. You are not using it at that time, and is thus a form of purification. Okay, whereas analytical, as the name suggests, this is associated with analysis. It is associated with analysis. Now herein you will be having this analytical chromatography. It is done normally with smaller amounts of material, and it is for establishing the presence or measuring the relative proportion of analytes in a mixture. So usually the analytical chromatography, it is carried out in lab scale, while you are trying to find out from a mixture how many components are there, or if you want to find out the specifics of an analyte, using which mobile phase you can segregate the analyte from the system and all these things. When you are in the trial stage, at that stage we usually use the analytical technique, so that we can establish all the protocols properly, and then when we try to go for the scaling up, we go towards the preparative chromatography. Okay. Now, chromatography terms, as I told you, analyte, it is the substance to be separated. Okay. The eluate is the eluted solute. So you have the chromatography system, the solid which is coming out, it is called eluate. It is called the eluate. Okay. The sample is the matter which is being analyzed in the chromatography. So the sample or the mixture which you are putting in, by dissolving it in the mobile phase, that is called the sample. In, it is called sample. Out, whatever the purified solutes you are getting, that is eluate. Okay. When the sample is treated in the course of the analysis, the phase or the phases containing the analytes of interest is or are referred to the sample, whereas everything out of interest separated from the sample before or in course of analysis is referred to as waste. That means apart from solute, you will be getting other mixtures also which may be say the impurities. So those impurities which are in lower concentration and it is not what you call it is not the compound of your interest, then it is called the waste. Okay. The bonded phase is a stationary phase that is covalently bonded to the support particles or to the inside wall of the column tubule. Okay. Then chromatogram, it is the visual output of the chromatograph. Okay. In the case of an optimal separation, different peaks or patterns on the chromatogram corresponds to different components of the separated mixture. A chromatograph or aerograph is the chromatogram when you are using gas as the mobile phase, is an instrument that enables a sophisticated separation. The eluate, it is the mobile phase leaving the column. So solute, it is the eluate, and the mobile phase, it is the eluate. Okay. So we are having, till now we are having two important components, eluate which is the solute, eluate which is the mobile phase which is coming out of the this chromatographic system, and we have the analyte which is basically the compound which we want to separate or purify. This eluate, it is also regarded as the effluent. Eluate, it is also regarded as the effluent. That means this mobile phase which is coming out, it is called eluate or effluent. So you can keep this in mind when we talk in terms of the industries. We say the effluent which is coming out, which are basically the waste system or the discharge system of the industry. Okay. So those are called effluent. Herein the system or the mobile phase which is coming out of the system, and it is not our what you call primary thing of or primary interest, thing of primary interest, hence it is called the effluent. Okay. Then eluent is the solvent that carries the analyte. So when it is within the chromatographic system, it is called the eluent. Okay. When the mobile phase, it is within the system, eluent. When it is coming out, eluate. Okay. An heliotropic series is a list of solvents that is ranked according to their eluting power. Okay. What does this mean? Suppose you want to segregate A and B from a system, from a mixture. Now, for this, you may be having analyte or the solution solvents, say 1, 2, 3, 4, 5. There are 5 solvents. Okay. Now, all of them, it may be dissolved in 1, 2, 3, 4, 5, and then we run the column. Okay. So, it is the ranking of these solvents depending upon the ability of these solvents to elute A and B in a proper manner, in a proper what do you call, you are able to separate this in a very systematic and a very purified manner if you are able to separate these two. And when you try to rank that series, it is regarded as the allotropic series, which is basically the ranking of these solvents, which basically tells you how these solvents will be able to separate the analytes A and B. Okay. Then, as I already told you, immobilized phase, it is called the stationary phase. Mobile phase is the phase that moves in a definite directions. Okay. It may be liquid in liquid chromatography and capillary electrochromatography. A gas in gas chromatography, a supercritical fluid in supercritical fluid chromatography, SFC. Then retention time is the characteristic time it takes for a particular analyte to pass through the system. Okay, that is called the retention time. Then detector, it refers to the instrument that is used for the qualitative and quantitative detection of the analytes after the separation. Now herein we have been given with typical chromatogram. Okay, and if you see, suppose we are having two components A and B. If you see in the first case, before the analyte A has been completely eluted, the analyte B, it has started to be eluted out of the system. Hence, if you see, there is a merging of the P. That means there is this elution, it is not a proper elution. Okay. However, the second case, if you see, after the complete elution of the analyte, the second peak has started. Here we will say that the chromatogram is a proper chromatogram, or proper separation of the analytes has taken place over here. Okay. Now, what are the factors which we can play with? The first factor is the mobile phase. Okay. As I told you, you can take the help of this allotropic series to change the mobile phase, and by changing the mobile phase, what you are doing? You are playing with the partitioning coefficient or distribution coefficient of the system, and by changing this partition coefficient and the distributing coefficient for a particular solute, you are basically changing the affinity towards the mobile phase and the stationary phase, and by using a proper mobile phase, you can achieve proper separation of the analytes. Okay. Second is that we can change the stationary phase. We can change the stationary phase. However, changing the stationary phase is quite costly. Okay, especially when we are dealing with much more efficient chromatographic techniques like liquid chromatography, gas chromatography, and so on. Okay. So in most of the cases, the changing the stationary phase, though technically it is possible, but physically it is not possible. Physically means practically it is not possible. Okay. So next, what you can do? The third step, it is again related with the mobile phase. We can change the velocity of the liquid of the mobile phase. Okay. When you are reducing the velocity of the mobile phase, what you are doing? You are reducing the drag what the B analyte would be experiencing, and if it finds a lower drag, then there is a possibility that the A will be eluted first, because it is more soluble in the mobile phase, and after it has been eluted, then the this mobile phase, it would be able to extract the B type of the analytes in a proper manner. Okay. Now here are certain terms which are there. Okay. Now what I have told you, sorry, we are having this chromatogram. Initially we will be getting a small peak, then we will be getting two peaks like this. Okay. The first one is for the mobile phase. Okay. The time when you have injected your sample to the time when you have got the peak of your what you call analyte concentration, that time it is regarded as TR, or the retention time. Okay. Now herein in the next, this in the point 2, I have discussed about adjusted retention time. Over here I have given TR minus TM. Now what is this TM? TM is nothing but the time duration for which your mobile phase was within the column. Retention time, it is the time for your analytes, say in this case analyte A, the time for which the analyte A has been retained within the column, it is called, say, TRA or TRB. Okay. So this was A, the second was B. So the first one would be TRA, the second one it would be TRB. Okay. Now the relative retention, the adjusted retention, so it would be TR dash, it would be equal to TR minus TM. TR minus TM. So this is your adjusted retention time, because it is expected that your mobile phase, it will come at the initial stage. So we are removing that factor from this analysis. Okay. Then we have the relative retention, which is the retention between the two systems, and it is given by alpha, and it is because and it is given by TR dash 2, which will be coming out at a later stage, divided by TR dash 1, which is coming early, and in that case, higher the alpha value, greater will be the separation. Okay. Greater the separation, in other terms, better will be the separation. Then we have the capacity factor. Now this capacity factor, it is given by T dash R divided by TM. So this is called the capacity factor, and it is given by K. So higher the K, the greater will be the retention of your analyte within the column. Greater will be the retention of your analyte within the column. So we have learned in this slide about the retention time, adjusted retention time, then relative retention time, which is basically the alpha factor or the separation factor, and lastly we have talked about the capacity factor K, which will give you an indication about the greater retention or the time of retention of your analyte within the packed column. Okay. Now, types of chromatography. There are different types of chromatographic techniques. The first one, based on the mechanism of the separation, adsorption, as the name suggests. What will happen? You are having the stationary phase S, so your analytes, they will be adsorbed onto the stationary phase. If the mechanism of separation is adsorption of the analyte, differential adsorption of the analyte on the stationary phase, then the chromatographic technique, it is regarded as adsorption chromatography. Partition chromatography, if you have this stationary phase and then overhead you have a very thin layer of liquid, okay, and then you are injecting the mobile phase having the analytes, and again the analyte, it may be liquid or the gas. So what will happen? The analyte, it may partition onto the thin liquid layer. So over there you can be having this partition chromatography. So it is also called the liquid-liquid chromatography. Okay. Then we have ion exchange chromatography. So in the ion exchange chromatography, we have the stationary phase. However, on this stationary phase, what we will be having? We will be having some pendant ions. It may be anions, it may be cations. If it is an anionic stuff, then it will be used for segregating cations and vice versa. Okay. So if you are having this A minus or the anionic resins, these stationary phases, they are regarded as resins. So if you are having anionic resins, then you will be using say B plus cations, which will be which can go and interact with the AB, and there will be an interaction, and temporarily this B plus ions will be interacting with the A minus ions, and they will be retained within the column or the stationary phase of the system, chromatographic system. And later on, when you have removed all the impurities from the system, then you can change the property of the ions by giving some rejuvenating your regenerating solvents, which will be able to remove the cations from the system. Okay. Then we have size exclusion chromatography. In the size exclusion chromatography, the analytes will be separated based on the size of the analytes. Okay. Usually what you will be having, you will be having the columns, then you will be having the beads. Okay. And within these beads will be porous in nature. So the larger analytes, they will not be able to move through this beads, and they will be moving out of the beads. So they will be eluted faster, whereas the smaller analytes, they will enter within this porous structure, and their effective path length will be increased, and hence they will be eluted at a later stage. Okay, so that is in size exclusion chromatography we work in that fashion. Then based on the mobile phase we can have liquid chromatography. In liquid chromatography we have normal phase chromatography and reverse phase chromatography. In normal phase chromatography your stationary phase is polar in nature, and in the reverse phase we have stationary phase as the apolar in nature. Then we have gas chromatography, then we have supercritical fluid chromatography. Okay, this is not there in our syllabus, so we will not discuss this one, but you should know that supercritical fluid chromatography, this terminology you should know. Okay, then based on chromatographic bed planar, that means your stationary phase it will be present as if it is a present as a plane, so there will be an XY direction. Okay, in the column chromatography you can have packed column or tubular column. So this stationary phase it will not be there, it will be, you will be having some this pendant groups which have been functionalized over the columns. Okay, so in this way we can have the packed or the tubular. So we will stop today. In the next class we will be discussing it.